When AC electrical power is applied for the first time, the aircraft runs through a set of system self-tests. The computers that feed the display units take a while to boot up, and the displays will be blanked until about 2 minutes after AC electrical power is applied. Additionally, you can hear the equipment cooling fans cycling in the background as they complete their own self-tests. The integrated standby flight display comes online almost immediately, but takes approximately 90 seconds to initialize. The ISFD receives airspeed and altitude data from a dedicated pitot-static air data module. Attitude data is provided by internal inertial sensors, allowing the ISFD to provide attitude information independently of other aircraft systems. The ISFD also receives ILS information from the center ILS receiver. It receives heading information from the same source as the captain's primary flight display. Note that although the initialization has completed now, and we now have attitude information on the ISFD, no heading information is yet available, as the ADRU is selected off and has not aligned yet. It's 40 degrees outside, and we do not yet have any air conditioning running on the aircraft. The prospect of finding your aircraft sitting dead at the gate with no air conditioning in 40-degree heat wouldn't go down too well in the crew room. It's extremely unlikely that you'd come across this scenario in the real world, but we're working with what we have here to bring you the cold and dark start. To add some semblance of realism, let's attach ground-conditioned air now. Before doing this, we need to check a couple of things. Before connecting ground-conditioned air, both pack switches should be selected off. This prevents automatic pack operation if bleed air is subsequently applied to the aircraft while ground-conditioned air is still connected. Remember that the packs are not required when using ground-conditioned air. The whole idea is that conditioned air is pumped directly into the cabin distribution system. Both recirculation fan switches should be selected off. This allows the ground air conditioning unit to operate at maximum efficiency. When we disconnect the external air later, we'll return these switches to their normal positions. Attachment and detachment of external air is done through the CDU on the PMDG aircraft. We can arrange this through any CDU, but let's use the center one for this purpose, so as to leave the other two to strictly flight-related actions. Open up the FS Actions menu, then Ground Connections in one right. Clearly we already have ground power connected, but we need to connect an air conditioning unit by pushing 5 left. The ground air conditioning unit feeds air directly into the mix manifold. It is then distributed around the cabin via the cabin air distribution system. With cool air coming out of the vents, we will now start the preliminary pre-flight procedure. This procedure assumes that the electrical power-up supplementary procedure has been completed. Select the ADRU switch on. 30 seconds after this switch is pushed, the ADRU begins alignment, and the position initialization process begins. ADRU stands for Air Data Inertial Reference Unit. The ADRU on the 777 has two main functions: air data and inertial reference data. The ADRU uses 6 laser gyros, 6 linear accelerometers, and inputs from several probes on the outside of the aircraft to calculate altitude, airspeed, attitude, heading, and position data. This data is outputted to a network of systems on the aircraft. The ADRU itself weighs over 30 kilograms and is located in the main equipment center above and behind the nose landing gear wheel well. It is a development and refinement of older systems that use separate air data computers and inertial reference units. ADRU combines these, allowing the number of line replaceable units in the main equipment center to be cut down to only 1. The ADRU is backed up by a secondary attitude air data reference unit. This provides secondary source of critical flight data and takes over automatically if the ADRU fails. The SARU is another line replaceable unit down in the main equipment center. ADRU alignment takes between 7.5 minutes and 15 minutes to complete. The time is a function of latitude. The higher the latitude, the slower the rotational velocity of the aircraft in space, so the longer the align time. Dubai is on the 25-degree north parallel, so we'd expect a shorter align time than in Keflavik, for example. After pushing the switch, verify that the on-battery light is extinguished and that the off light is extinguished on the ADRU switch itself. We now need to check various items on the status page. The status page is a multifunction display format. The MFD can be displayed on either of the 2 inboard display units, or on the lower center display unit. There are many MFD formats selectable from the Display Select panel on the first officer's end of the glare shield. The three switches at the top of the panel allow the pilot to select which display unit responds to the mode select switches below. Each switch has a light above it that illuminates when the switch is pressed. The three select switches are latched electronically so that only one is active at any one time. To demonstrate this, let's display the status page on the first officer's inboard display unit. Select the right inboard display switch, then push status to display the status page. The status page shows information that can help you make a decision on the dispatch status of the aircraft. It shows hydraulic, APU, and crew oxygen information. The APU information is blanked when the APU is not running, as in this case. Take note of the hydraulic quantity and crew oxygen pressure and ensure that they are sufficient for flight. 1 is the normal service level for hydraulic quantity. Note that the pressure is very low, as no hydraulic pumps are running at the moment. The crew oxygen cylinders each hold 3,150 litres of oxygen at 1,850 psi, so the indicated values are reasonable. Note that our aircraft is fitted with chemical oxygen generators for the cabin, so only crew oxygen pressure is shown. An aircraft with a gaseous oxygen system for the cabin would have a passenger pressure display here too. We also need to check and verify any status messages present. Status messages have a relation to conditions that affect dispatch. Applicable publications are then used to make a decision on the dispatch status of the aircraft. TCAS is the only message here at the moment, and is to be expected. Select the secondary engine display and check the engine oil quantity. 26 quarts is normal and sufficient. Blank the MFD when you're done with it. I'll configure the display select panel to bring up the MFD on the lower center display unit next time we call for it. The remaining items on the preliminary pre-flight procedure are to be done after a crew change or maintenance action. We've picked up a cold and dark aircraft, so we'll continue with the remaining items. Various maintenance documents are to be checked before flight. This isn't really relevant in our case, so we'll omit this item. There are several items of emergency equipment on the flight deck that must be checked before flight. There is a halon fire extinguisher located behind the captain's seat. Halon fire extinguishers are effective on all types of fires, but are used primarily on electrical, fuel, and grease fires. There is also a crash axe located beside the fire extinguisher. An escape rope is fitted above each seat for egress through the number 2 windows in an emergency. One end of the rope is attached to the aircraft structure, and the other end is coiled and stored in a stowage bag. The rope and the stowage bag are to be thrown out of the window together. The bag will fall free. The crew member can then use the handholds on the rope to assist egress. Moving on for the emergency equipment, head up to the overhead maintenance panel. This panel houses controls that are set on the ground before takeoff or during ground maintenance. They should not require in-flight adjustment. Verify that all lights on the overhead maintenance panel are extinguished. All switches should be guarded, and the cargo temperature switches set as required. Check that all circuit breakers are pushed in, and that any popped breakers have a tag around them to identify them as systems that have been isolated intentionally. It's helpful to try to look across the circuit breaker panel rather than directly at it head-on, as popped breakers are more apparent from this perspective. The parking brake can be set at this time. In the real aircraft, the parking brake is set by depressing the brake pedals, pulling the parking brake lever, then releasing pressure on the pedals. This latches the brake pedals in the brake's applied position. The latch switches send a signal to close the parking brake valve, which prevents brake pressure leakage through the normal anti-skid valves. Once the parking brake has been set, it is prudent to check the brake accumulator gauge to ensure that there is sufficient pressure in the system and the brakes will hold. The brake accumulator supplies brake pressure to the system if there are no other brake sources. It should supply enough pressure for 6 full brake applications. Crucially in this case, it is the sole pressure source for the parking brake system when the hydraulic systems are off, and is designed to supply enough pressure to keep the parking brake pressurized for 8 hours. Some airlines call for the parking brake to be released whenever the aircraft is chocked. Others leave the parking brake set, even while the aircraft is chocked at the gate. At this point, once we've settled into our seat, it would be wise to take down the ATIS. This would typically be done on the VHF-2, with VHF-1 used for ATC communications. Tune the Dubai ATIS 131.7 in VHF-2 and monitor it on your headset.
Dubai International Arrivals Departures Aerodrome Information, Quebec. At time 0600. Arrivals runway 12 left. Airfield information. Expect ILS approach. Departure runway 12 right. During pushback and taxi, squawk assigned transponder code. After receipt of clearance, pilots must report ready for pushback with delivery on frequency 120.35. Surface wind 180 degrees, 6 knots. Varying between 140 degrees and 220 degrees. Cab OK. Temperature 40. Dew point 16. QNH 1005 hectopascals. No significant change. Advise ATC that you have copied information Quebec.
We will now move on to the pre-flight procedure. This is a split responsibility procedure between the captain and the first officer. Each crew member has his own specific scan flows. We've modified the flows for single pilot operation, skipping some items on the first officer side of the flight deck, yet including his main areas of responsibility to permit full operation of the aircraft. The pre-flight procedure begins at the top left of the overhead panel and flows down it in a waterfall pattern. We start at the thrust asymmetry compensation switch, which should be in the auto position. Thrust asymmetry compensation, or TAC, is a function of the fly-by-wire system on the 777. TAC applies rudder and rudder trim input automatically in response to asymmetric thrust. This significantly reduces the yawing and rolling effects experienced after engine failure, and reduces the severity of uncommanded flight path changes. In keeping with Boeing's flight control philosophy, TAC does not fully compensate for the failed engine, in order to aid recognition and keep the pilot in the loop. TAC authority is limited to 60% of available rudder. With the thrust asymmetry compensation switch in the off position, TAC is inhibited. The switch should be at auto for normal operations, allowing the system to operate automatically if a thrust asymmetry condition of greater than 10% is detected. Confirm that the primary flight computer's disconnect switch is guarded. The aircraft has 3 primary flight computers, which calculate flight control commands based on pilot inputs, control laws, and flight envelope protection functions. These are the heart of the fly-by-wire system. Selecting the primary flight computer switch to the disconnect position disconnects the PFCs from the flight control system, forcing the system into direct mode. In direct mode, the pilot control inputs are sent directly to the control surface actuators. The switch should be guarded, forcing it to the auto position. This allows the system to operate in normal mode, but degrade to the secondary or direct modes automatically if sufficient system faults occur. Verify that the disconnect light is extinguished. If this were illuminated, it would indicate that the system is in direct mode. Moving down to the electrical panel, confirm the following. The battery switch should be on, with the off light extinguished. The off light illuminates when the battery switch is off and the aircraft has AC power. The IFE passenger seat switch should be on, and the off light should be extinguished. This switch controls the electrical power to the in-flight entertainment system, as well as power to the passenger seats. Passenger seats draw power from the electrical system for motorized movement, power outlets, and telephones. This switch also controls power to the flight deck entry video surveillance systems if fitted, as well as the ground maneuver camera system on the Dash 300 and the 300ER. The cabin utility switch should be on. This is commonly regarded as one of the most important switches on the flight deck, as it has a direct influence on the tea and coffee supply. This switch controls electrical power to the ground service bus, utility buses, and crucially the galleys. When selected off, it also removes power to the beacon, logo, and wing lights, as well as forcing on some cabin lights. The APU generator switch is left on, even when the APU is shut down. In the on position, the APU generator control unit is armed to control APU generator electrical power automatically. The off light should be extinguished at this time. It illuminates when the switch is out, or when the APU is running, yet has been disconnected from the electrical system for any reason other than the application of secondary external power. Both bus tie switches should be at auto. These switches control the operation of the 2 bus tie breakers that allow isolation of the 2 sides of the AC electrical system. The generator control switches function similarly to the APU generator switch. In the on position, The generator control unit is armed to control IDG electrical power automatically. The off light illuminates when the switch is out, or when the related generator circuit breaker is open. Like the APU generator switch, these switches are normally left on, even with the engine shut down. The drive disconnect switches should be guarded, and the drive lights illuminated at this time. These switches allow mechanical disconnection of each IDG from its respective engine. The drive light illuminates when the related IDG has low oil pressure. The engines are currently shut down, so low IDG oil pressure is to be expected. The backup generator switches should be on, and the off lights illuminated. Each engine has a backup generator that can supply 115 volt AC power to the transfer buses. Each backup generator contains 2 permanent magnet generators that supply power to the flight control DC electrical system. The off lights remain illuminated until the respective engine is shut down. Move down to the left wiper selector and verify that it is off. Moving back up to the top of the overhead panel, the ground proximity runway override switch should be off. Honeywell's Runway Awareness and Advisory System assists flight crew awareness of aircraft position during ground operations, approach to landing, and go around. This switch allows the crew to inhibit the system where required. There is no good reason for us to inhibit it on this flight, so the switch should be off. Close the guard on the emergency light switch. This forces the switch to the armed position, allowing all emergency lights to illuminate if there is no power on the left and right main DC buses. The armed position also allows a limited number of lights to illuminate when a passenger entry door is opened in the armed mode. Selecting the switch on forces all emergency lights to illuminate. The off position prevents emergency light system operation, even if aircraft electrical power fails or is turned off. The previous crew selected this switch off as part of the secure procedure to prevent activation of the system when they powered the aircraft down. Armed is the normal position for flight. The service interphone switch should be off. The service interphone system provides voice communications between various ground crew stations around the aircraft. The flight interphone system provides voice communications between the flight crew and ground crew plugged into the flight interphone jack in the nose landing gear wheel well. With the switch in the on position, these two systems are connected. Selecting the switch off allows independent operation of the service and flight interphone systems. Off is the normal position. Verify that the passenger oxygen on light is extinguished. If the on light is illuminated, the passenger oxygen system is operating and the masks in the cabin have dropped. This aircraft is fitted with a chemical passenger oxygen system, meaning that passenger oxygen is supplied by individual chemical oxygen generators rather than bottled gaseous oxygen. The masks drop automatically if cabin altitude exceeds approximately 13,500 feet, but can be manually deployed using this switch if required. For the sake of your maintenance crew, leave this switch guarded. Replacing the rubber jungle in the cabin is not an enviable task. All 4 window heat switches should be on. All 6 windows on the flight deck are heated to prevent fog and ice buildup. 2 window heat control units in the main equipment center control the window heat system, and backup circuits provide redundancy for heating the number 1 windows if either window heat control unit fails. Power output to the windows is reduced during the first 4 minutes of operation to reduce thermal stress due to heating. Overheat protection is automatic. The in-op lights illuminate if the switch is off, an overheat is detected, or a system fault has occurred. All 4 inoperative lights should be extinguished at this time. Moving down to the hydraulic panel, verify that the ram air turbine unlocked light is extinguished. The ram air turbine, or RAT, is an air-driven generator that provides emergency source of hydraulic and electrical power for the primary flight controls. The ram air turbine propeller diameter is approximately 105 cm and is governed to rotate at approximately 4,510 rpm. The RAT deploys automatically in a dual-engine failure scenario when center hydraulic system pressure is low. It also deploys in flight when both AC transfer buses are unpowered or all 3 hydraulic system pressures are low. It can also be deployed manually by pushing the ram air turbine switch. Subsequent illumination of the pressure light indicates that the ram air turbine is deployed, and center system primary flight control hydraulic pressure is greater than 1500 psi. The unlocked light illuminates if the ram air turbine is not in the stowed position. The rat should be stowed during all normal operations, so the unlocked light should be extinguished. Verify that the left and right engine primary pump switches are on. With the switches in the on position, each engine-driven hydraulic pump will pressurize its respective system when the engine rotates. Both fault lights should be illuminated, correctly indicating low primary pump pressure at this time, as the engines are not running. The Center 1 and Center 2 electric primary pump switches should remain off with their fault lights illuminated. If these switches were selected on, the center hydraulic system would pressurize, and for safety reasons we need to wait for the go-ahead from the ground crew before pressurizing hydraulics. All 4 demand pump selectors should be selected off, and all fault lights verified illuminated. Again, this is an indication of low demand pump output pressure at this time, which is to be expected with the pump selected off. On the passenger signs panel, notice that there is no smoking selector fitted. It's been many years since smoking was routinely permitted on passenger flights, and many airlines have had this selector removed. Some have chosen to replace it with a no electronic selector, or simply a no smoking selector that is forced on at all 3 positions. What we do with the seatbelt selector at this point is dependent on our refueling status. If the aircraft is being refueled, the seatbelt sign must remain off, and passengers reminded not to fasten their seatbelts, lest an evacuation be required. If refueling is complete, the seatbelt sign selector can be selected to auto or on. The auto position uses system logic to set the seatbelt signs on or off automatically. With the selector in the auto position, the seatbelt signs are switched on whenever the landing gear is not up and locked, the flap lever is not up, aircraft altitude is below 10,000 feet, or cabin altitude is above 10,000 feet. The seatbelt signs also illuminate automatically whenever passenger oxygen is on. Given the system logic, there is effectively no difference between the auto and on positions when the aircraft is below 10,000 feet, as the seatbelt signs are forced on automatically. On a fair weather day with no expected turbulence, some crews might elect to leave the selector in auto and allow the aircraft to switch the signs off automatically passing 10,000 feet. More common, however, is the decision to select the signs on, then switch them off manually as part of a flow at 10,000 feet. This removes the possibility of the signs switching off automatically, when it might have been more prudent to leave them on due to unexpected turbulence. We will take the safer policy and select the seatbelt selector to on at this time. Moving down to the lighting panel, all interior lighting rheostats should be in the mid position. The master brightness switch should be selected on. The switch is on when it's pushed in, and when the switch is off, a black ring is visible around it. Selection of this switch to on allows the master brightness control system to control the brightness settings of many displays, instruments, backlights and floodlights around the flight deck. Individual lighting controls have a center detent position identified by a white dot at the mid-range position. With individual controls set to the white dot position, the master brightness control can then be used as needed to set the brightness level. We will discuss this in greater detail when operating the aircraft at night. The landing light switches should be off at this time. The aircraft has 1 landing light in each wing route, and 2 landing lights on the nose gear strut. The wing landing lights are optimized for flare and the ground roll, while the 2 nose gear landing lights are optimized for approach. The wing landing lights illuminate bright when the gear is down and locked, and dim otherwise. The nose gear landing lights do not illuminate when the nose gear is not down and locked. Back up to the top of the overhead panel, verify that the APU bottle discharge light is extinguished. A pressure switch in the APU fire bottle detects when pressure drops below a certain threshold. This is a clear indicator of bottle discharge and illuminates the APU bottle discharge light. Verify that the APU fire switch is in and that the red fire warning light is extinguished. The APU fire bottle can be discharged manually by pulling this switch and rotating it in either direction. Both cargo fire arm switches should be off, and both cargo fire warning lights extinguished. Pushing the cargo fire arm switches arms the cargo fire protection system, and configures the air conditioning system to discourage the spread and build-up of the fire and smoke. In the case of an aft cargo fire, this also activates the lower crew rest evacuation system. The cargo fire extinguisher bottles are discharged by pushing the cargo fire discharge switch. verify that the cargo fire discharge light is extinguished. Moving down to the engine panel, verify that both EEC mode switches are at normal. EEC stands for Electronic Engine Control and uses data from engine sensors and aircraft systems to control engine operation. A more commonly used term in the aviation industry is Full Authority Digital Engine Control, or FADEC. This better describes the concept of computers having full authority over control of the engine, and the fact that the pilot has no mechanical connection to the engine himself. With the EEC mode switches in the normal position, the EEC is in normal mode. In normal mode, the electronic engine control uses N1 corrected for inlet temperature as the main thrust parameter for controlling engine thrust. The system can degrade to the soft alternate mode automatically due to system failures, or can be degraded manually to the hard alternate mode by pushing the EEC mode switches. In alternate mode, the electronic engine control uses N1 and thrust lever angle to control the engine thrust. Normal is the position for normal flight. Both start switches should also be in the normal position. Note that the start selectors on this particular aircraft do not have a continuous position. Continuous ignition is controlled automatically. Verify that the auto start switch is selected on. This arms the auto start system, allowing the EEC to control fuel and ignition during engine start. A manual start is possible by selecting the auto start switch off and following the manual engine start supplementary procedure. For an automatic start, the off light on the switch should be extinguished. On the fuel jettison panel, verify that the fuel jettison nozzle switches are off and the valve lights are extinguished. The fuel jettison system dumps fuel overboard, reducing aircraft weight and permitting a landing below the maximum landing weight. Illuminated valve lights would indicate that the corresponding jettison nozzle valve is not in the selected position. The valves are commanded closed with the switches in the off position, so the valve lights should be extinguished at this time. The fuel to remain selector allows manual control of the fuel to remain quantity at which the system will stop jettisoning fuel. The selector should be pushed in for automatic selection of the maximum landing weight fuel to remain quantity. The fuel jettison arm switch should be off. This disarms the fuel jettison system. Additionally, the fault light should be extinguished. On the fuel panel, verify that the crossfeed switches are off. In the off position, the flow bar on the switch is not visible, and the crossfeed valve is selected closed. The fuel system is designed such that any fuel tank pump can supply either engine. The crossfeed valves are closed during normal operations and isolate the left and right sides of the fuel system. Either valve can be opened to feed an engine from the opposite tank. This is done by pushing one or both of the crossfeed switches, exposing the flow bar. An illuminated valve light indicates that the crossfeed valve position does not agree with the position of the switch. The valve light should be extinguished. All fuel pump switches should be selected off, regardless of whether or not the APU is running. In our current state, all main tank boost pump pressure lights are now illuminated, as the pumps are not running and output pressure is therefore low. The pressure lights on the center tank fuel pump switches are inhibited when the switches are selected off, so these are extinguished. With the APU running and AC power available, the left forward fuel pump operates automatically, regardless of the position of the switch. In this case, the corresponding pressure light would be extinguished, but the APU isn't running in our case, so it's illuminated. The 200 LR variant of the 777 can be fitted with an auxiliary fuel tank that can be made up of either 1 or 3 cells. Our aircraft today does not have this option, so there is no auxiliary fuel switch fitted. The wing and engine anti-ice selectors should be set to auto. The 777 has an ice detection system that controls the wing and engine anti-ice automatically based upon inputs from 2 ice detectors, one on each side of the forward fuselage. With the switches in the auto position, wing and engine anti-ice valves are opened or closed automatically by the ice detection system. Note that the automatic ice detection system is inhibited on the ground, and we'll talk more about that later. Moving down to the lighting panel, confirm that the beacon, runway turnoff, taxi and strobe light switches are selected off. As explained earlier, the navigation light should be selected on whenever electrical power is applied. The logo and wing lights are not required during the day. The logo lights are fitted on the horizontal stabilizer and illuminate the airline logo on the tail. The wing lights are installed in the fuselage and illuminate the leading edge of each wing. The indicator light switch can be selected to bright or dim to set the brightness of all illuminated annunciator lights. The spring-loaded test position illuminates all annunciator lights on the flight deck to full brightness for 10 seconds to allow check of the bulbs. The lights then dim for as long as the switch is held. The test position also causes test patterns to display on the stabilizer position indicators, the rudder trim indicator, the radio tuning panel displays, and the mode control panel. Move back up to the top of the overhead panel again, this time to the air conditioning panel. The equipment cooling switch should be at auto. This allows automatic control of equipment cooling. Pushing the switch manually sets the mode of operation to override, resulting in reduced equipment cooling, among other side effects. Equipment cooling can also degrade to the override mode in the event of failures. In this event, the override light will illuminate. It should of course be extinguished at this time. The gasper switch should be selected on. The gasper fan pulls air from the passenger air distribution system and directs it to gasper air outlets above each passenger. These of course are the adjustable air outlets you might be familiar with as a passenger. With the switch selected off, the gasper fan does not operate and these outlets will not supply any air. The recirculation fans return cabin air to the distribution system, filtering it in the process. About a half of the air in the distribution system comes from the recirculation fans. This reduces bleed air demand on the engines, saving fuel. These switches should be selected on normally, but as we have ground air conditioning connected, we will leave them off for the time being to allow the ground air conditioning unit to operate efficiently. Set the flight deck temperature control to the mid-auto position. This provides automatic temperature control for the flight deck. Turning the control towards cold or warm sets a target temperature. The temperature range is between 18 Celsius and 29 Celsius. The mid-12 o'clock position sets approximately 24 Celsius. The flight deck receives air from the left pack and is maintained at a slightly higher pressure than the passenger cabin to prevent smoke and odours from entering the flight deck. The cabin temperature control functions similarly. Turning the control towards cold or warm sets the master temperature for the passenger cabin between 18 Celsius and 24 Celsius. This should be set in the mid position. The cabin crew can adjust the target temperature for each zone in the passenger cabin. The temperature that they select can be up to 6 Celsius higher or lower than the value set by the flight crew. Both pack switches should be at auto for normal operations. This allows automatic operation of the pack flow control valves to control pack airflow. Single pack operation on the ground results in similar fuel consumption compared to two-pack operation, but causes higher flight line noise levels as a single pack must work harder than two working together. Since we have ground air conditioning connected, we will leave both pack switches off for the time being to inhibit automatic operation of the packs. The pack off lights will remain illuminated until the packs are selected on later and have sufficient bleed air pressure to run. Both trim air switches should be on. The packs supply air at a fixed temperature to the mix manifold, after which it is sent to the passenger cabin. The trim air system mixes warm air from upstream of the packs with cold air from the mix manifold to keep each cabin zone at its target temperature. Selecting either trim air switch off closes the respective trim air valve. Flight deck and cabin temperature control without trim air is much less accurate, so the trim air switches should remain on during normal operations. Verify that the fault lights are extinguished. The left, center, and right isolation switches should be set at auto. This allows automatic control of the 3 bleed air isolation valves. These valves allow the 3 air sources to be isolated from one another. Pushing one of the switches commands the respective valve closed and illuminates the closed light. The closed light also illuminates whenever the system closes the valve automatically, or if it fails closed. Detection of a duct leak or bleed loss, for example, would cause the system to close the valve. The closed light should be extinguished at this time. The engine bleed switches should be selected on. This arms each engine bleed valve to open when the engine bleed air is available. The off light should be extinguished. Illumination of the off lights indicates that the respective engine bleed valve has been closed, either manually or automatically. The APU bleed switch should be at auto. With the switch in this position, system logic will open the APU bleed valve automatically when bleed air pressure is available. The off light should be extinguished. Illumination of the off light indicates that the APU bleed valve has been closed, either manually or automatically. On the pressurization panel, verify that the outflow valve switches are at auto. The 777 has two outflow valves, one forward and one aft. Typically, most of the airflow is through the aft outflow valve. This improves ventilation and smoke clearance. The two outflow valves can be controlled independently of one another, and either valve can maintain cabin altitude and full ventilation rates alone. Pushing either switch reverts the respective outflow valves to manual control, bypassing the automatic outflow valve control and cabin altitude limiter. Manual control of the switches is then possible using the outflow valve manual switches below. Each valve takes approximately 20 seconds to open or close completely in the manual mode, but in the automatic mode is much faster and takes less than 10 seconds. The switches should be left in auto for normal operations, as no specific flight crew action is required for fully automatic operation, provided that the FMC data is valid. In automatic mode, the cabin altitude controller uses ambient pressure and flight plan data from the FMC to calculate a cabin pressurization schedule. This includes the destination landing altitude. The crew can specify landing altitude manually by pulling out the landing altitude selector and then turning it to set the value on the ICAS. For normal operations, this switch should be pushed in. To finish the scan flows on the overhead panel, confirm that the right wiper selector is off. Ordinarily, the first officer would have completed the overhead panel scan flows and would now set up his end of the mode control panel, the display select panel, and the EFIS control panel. He would then check his oxygen mask and flow up around the right forward panel before moving down past the landing gear lever onto the control and aisle stands. PMDG gives us the